So I'm here showing you the spreadsheet to solve homework number 2. And I have two solutions, just in case. If you assume to be compression, I'm gonna have here the solution. If you assume to be tension, I'm gonna have the solution. So you're not gonna be losing points if you assume tension versus compression. But the right way of doing it, because we have here pre-stress, is gonna be compression, right? Let's say that I'd like to take this problem here and use it here, right? And apply it here. And I'm gonna be doing here 6 skips. Now, do I have any moment? Just wondering, do I have any moment with the 6 skips? Moment is gonna be equal to what? 6 multiplied by 8 inches, right? 8 inches. So what I can do here, here's compression is gonna be 6, and this gonna be 6 times 12 minus 4 is gonna be 8 divided by 12, because I need to have it as in kip-foot. Section properties, you can say, for example, the top piece, which is a flange, is gonna be, the width is gonna be 16 by 12, and the bottom piece is gonna be also same thing. So for the width is gonna be 16, depth is gonna be 12, and here's gonna be 16, another 12. Look what happened. Why top and bottom? It's gonna be right in the middle. So this time to the real question. Can I just assume it, or can I still use this spreadsheet? I can use this spreadsheet, and if you assume compression, this is gonna be the stress that you're gonna be getting, right? Just from the compressive force is gonna be equal to that much. 6 divided by the total cross-section area, which is the same as this. What I'm trying to say here, try to develop your spreadsheet if you didn't do it yet. It's gonna help you out on all problems that you're gonna be doing here. It's gonna make your life much easier. And then after that, you can just copy these values, right, to your solution. It's gonna be very good to confirm your answer. At least if you like to confirm your answer, you can do it with the spreadsheet and be sure that you're doing it correctly, instead of just sweating and spend time trying to make it work, and you feel that, well, maybe I did it, maybe I couldn't, and this type of struggle. So I don't want you to struggle. This is why I do a spreadsheet for yourself. Continue with our business after we were able now to do the stress top and bottom. Right? So this is going to be the homework. The homework is going to be based on this analysis. We discussed the issue of having self-weight to call it dead load, and then superimposed dead load is going to be any additional dead load, and then also the life load to call it total. And you understand that we're not trying to solve here for female. We're trying to do here some service analysis, check on the stresses and so forth. And then we said that we can use this equation. This gives you the basic equation that we can use. And then we evolved it to this way of looking at it. We call this the basic concept method. And in all of these equations, PI, AC, E, C sub T, R squared, MD, and ST, all of that's going to be positive values. And all of the signs that you're looking at will take care of putting it into tension to be positive and compression to be negative. So from now, if you look at any stress, it's going to be negative in your analysis, means compression, and any positive stress is going to be tension. And we're going to be following these equations. Also, we said that this PI is going to be the initial pre-stress. This is when you start to do the pre-stress, it's going to be this PI. Eventually, it's going to be PE. Now, which one's larger? Of course, when you start, the stress is going to be larger, and then after that, you're going to have some losses. We see losses, it could be 15 to 20%, sometimes 12%, depends on the aggregate, the cure time, the moisture, the environment that you're going to put the pre-stress in, the type of anchorage. You have many sources for this losses. As we said, the first term here is going to be based on the amount of pre-stress and the beam properties, the beam section. And this second term is going to be about the self-weight of the beam itself. So this represents here the self-weight of the beam, and this represents the pre-stressing effect. Pre-stressing effect, it has two components. One of them is going to be based on the axial force, which is Pi over AC, and the other one is going to be for the amount of eccentricity, E, the distance from the centroid of the section to Pi, to the location of the pre-stress. Now, the beam has hardened, and we already transferred the pre-stress force, and this at this point here, we call this transfer of the pre-stress force at the initial point, Pi. Now, at the surface level, which means when you start to use the beam, the Pi now has dropped to the effective pre-stress, P sub E, which is going to be lower, slightly lower than Pi. But the applied load is going to be just M dead load. It's going to be M dead load plus M superimposed dead load plus M life load. So I have here two cases. One case right at the transfer of the pre-stress force, and the second case at the service level, or service case. At the service case, we're going to have PE, and then we're going to have M total. PE is going to be the effective pre-stress. At the transfer time, or the initial pre-stress, we're going to have only the pre-stress force, and when it comes to the external applied load, it's going to be only the self-weight of the beam. Does this make sense? Yes. Now we are aware of the time of transfer, which is SPI, and also we are aware of the load that goes with it, external load. But when it comes to the service case, we're going to have PE, which is going to be slightly lower. We're going to have the total load. And in each one of these two cases, we need to find out the stress top and bottom and check this against some allowable stresses by the code. So this is not Feynman. This is not the strength design. This is to figure out the stresses within the pre-stress beam and whether it's going to be allowed or not. Now, we understand that we're going to be draping the cable. Draping the cable means cable is not going to be straight. We're going to bring it down at a certain point. It can be just at one point like this, which we call harping, or it can be draping like this. It depends on the way that you are building it, the way that you build the beam. If you do pre-tension, which means tension force is going to be applied before you start to pour the concrete, and you'd like to change the profile of the cable, in that case, this is going to be the way that you'd go with. Why? Because you're going to have only one point load here, or like a mechanism or a kind of a tie is going to bring this piece and just anchor it to the floor. You're going to bring something there, you're going to put it there, it's going to be bringing this down. It's going to be like a hold down, right? Because in pre-tension, you cannot afford to do it this way. It's really hard because you cannot just put one point here, another point you're going to bring it here. You cannot make it that uniform, right? You cannot. It's going to be very tough. So in pre-tension, you just do one point. In post-tension, you can do this because you can just drape the cable, you put it in this profile, and then later on, after the concrete harden, you're going to start to do your tensioning. So this is the reason that in one case we do this harping, which is most likely for pre-tension, and this most likely is going to be for post-tension. Now let's look at the stress distribution and what's going to happen over this process. So I'm going to be looking here at case A. Here is a kind of irregular beam, like a standard typical beam that you are going to be doing the pre-stressing on. Here is going to be the initial pre-stress. What does it mean by initial? It's going to be at the time of transfer. So I'm going to enlarge this and bring it in. This red line would represent, this here represents the datum for the stress distribution. Here's the beam section. We have C top, C bottom. Sometimes you call it Y top, Y bottom. There's nothing wrong. You can use either one of these two symbols, Y or C. Amount of pre-stress that you have here is going to be called PI because it's going to be initial pre-stress. Because of the axial force that you have over this section, you're going to have PI over AC over the cross-section area of the concrete. It's going to be uniform stress. Also, because of this eccentricity, you're going to have additional moment, like very similar to what I've just showed in the example, right? When I put P times E. So if you take this force times E, is going to give you some moment. And this moment, you need to take it divided by moment of inertia multiplied by C top, which means divide here by S top to get the stresses right here. Repeat the same process here and do it at the bottom. So the whole thing that you're looking here at, this is going to be only for the pre-stress effect. You're going to have an axial component and some moment from this eccentricity. When you add them to each other, you're going to end up with this stress distribution. You'd expect that at the bottom, you're going to have lots of compression. On the top, you may end up with maybe some little tension. If this is stress value, if this numerical value is higher than this, or if this axial compression effect is more than this tension on the top from the bending, you may end up with little bit of compression. Are you good? Questions? Yes, questions or no?
Nothing.
You're good. So this stress distribution, I'm going to say, in this case, I'm going to say this is stress plus this is stress equals the final stress. I'm going to put this here. The final stress due to both combined of axial plus moment from the pre-stressing. Now, I'm going to assume here that this beam is sitting flat on the floor. Now, I'm going to start here to put the self-weight. I'm going to start to provide supports. So what's it going to do? Now, what I need to do is to take this stress from this shape distribution and just throw it here. Just copy it here. And add additional stress to it. Let's see, what should I add? I'm going to say here, you're adding the self-weight. The self-weight is going to be called M dead load. Divided by S top is going to be compression, and here's going to be M dead load divided by S bottom is going to be tension. And for that, you're going to be gaining the stress is going to be like this. So what did we do? We start to add the stress value here to that stress value. Same thing here. So here, I had some tension, the bottom compression. So here I have some tension, bottom is going to be compression. From the self-weight, I'm going to end up with some compression on the top and some tension on the bottom. So here you have some tension. You subtract this little bit of compression. You may still end up with some tension on the top. So top of the beam here is going to be exposed finally to some tension. Of course, it depends on your design, right? It depends on the value of the pre-stress that you put there and the amount of eccentricity. If this eccentricity is going to be very small, this moment is going to be small, and this tension is going to be small. But what we picked here, that was our choice in our analysis, that I put big enough eccentricity that I end up with some tension on the top. When I added some compressive stresses from the dead load, at the end, I still have some tension on the top, but this tension is not that big. And of course, in here, as you look here, I still have some compression because the amount of compression coming from the pre-stress force here was higher than the effect of the tension coming from the dead load. Are you good? Any questions or are good? Are you guys there?
We're good, Professor.
All right, thank you. Now let me take this stress distribution and let me see what happened here. This stress distribution includes PI, the pre-stress, initial pre-stress, the high value. Now the pre-stress is going to drop. So what does it mean? And instead of having this PI, now it becomes PE. Look at what happened here. Now I need to use this equation, exactly this equation, but replace PI with PE. Because now it's going to be, the losses has taken place. Now let's take it and start to apply the additional load. I'm going to say what additional load? I'm going to say here, I have three loads. I have dead load that you apply on the top, and then I have superimposed dead load, and then I have, which is additional dead load, and then I have life load. So this one, I'm done with it already, with this dead load. So what I still have is going to be the superimposed dead load and the live load, and you can see them right there. This applied load is causing compression, lots of compression on the top and lots of tension on the bottom. Let's add this tension to this compression, you end up with some compression. At the bottom, I'm going to end up with some tension. And I'd like to compare this with the conventional concrete. What's going to happen for the conventional concrete? In conventional concrete, this is going to be your stress distribution. You're going to have this much compression and this much tension in the top of this stress. You see this and this, right? If you add this together, dead load plus superimposed dead load plus live load divided by S top. In conventional concrete, this is going to be the amount of stresses, and the compressive would have been much higher than this value here. So what reduces this value? What reduces it was this amount of tension that you put in there. So before you apply compression on the top from the applied load, what you're doing here, right, based on this from the pre-stress, you apply compression at the bottom, tension at the top. So when the loads come, when all of this load is going to be coming into the picture, and you apply them onto the beam, at the beginning, you start with tension at the top, compression at the bottom. Now the loads, they're going to be causing compression at the top and tension at the bottom to counteract the effect of the pre-stressing that you started with. So actually, this is a good idea because you're adding here more capacity, you're adding more room for the stresses. Because guess what's going to happen? If you didn't start with this pre-stressing and you start to apply this dead load and superimposed dead load on live load, the stress would have been big, so big compared to the allowable stresses. And same thing is going to be for the tension. And this is going to be the benefit of having the pre-stressing. Please feel free to stop me at any time and ask the question.
So, Professor, on the graphs, if it's wider along the bottom of the neutral axis, that means it's under compression, right? If that area is bigger along the bottom. So, for example, on the right side of that.
Right side is compression, on the left side is going to be tension, right? Let's make it like that. Yes, but continue please with your question.
Oh, what was that? So left side is compression, right side is tension.
This one is compression, right? This side is compression. The right side is compression. So this compression, this is going to be tension. You see where the datum is at? This is going to be compression here. The other side is going to be tension. From this axial load, I have only compression. From the moment, I'm going to have here some compression and here's going to be some tension, right?
Okay, that makes sense. I was kind of going based off what's bigger, yes. What's smaller. Okay, awesome. Thank you.
Okay, no problem. Good question. Thank you for asking this. Very good.
Thank you.
Therefore, I have here two cases, right? I have at the time of transfer and then at the service time when you start to use a beam. At the time of transfer, you have PI. And which moment you have? You have moment due to dead load. And you can safely use these two equations. And this is what now you can start by putting your spreadsheet and do this. Your M dead load, you can put the dead load, you can put the span, figure out M is going to be W squared divided by 8, like the standard equation. Mostly we're going to have just simply supported beams in pre-stress. We're not planning to go into continuity and continuous beams. Now, at the service case, we're not going to have PI, we're going to have different value. It's going to be slightly less than this by 20%. But E and CT and R squared and all of this stuff is going to be the same. But instead of having M dead load, we're going to have M total. M total is going to be coming from M dead load, M superimposed load, like what we have here, and M live load. You just add them all together, and then you do check on the stresses. That's why we have another two equations. Okay. Just to be sure, this is going to be like the last step that we have there. Which last step? I'm talking about this step. Just have a clear on here slide, so this is more clear. It's going to be based again on the effective, right? cross-section area of the concrete, which you can put it as a value if you like. So you don't really need to do it for rectangular section unless it's gonna be rectangular section. So be sure that your spreadsheet is gonna be able either to take rectangular section, a T section, or just a value. You put the cross-section area as an AC. I'll tell you the reason. When you open the manual for pre-stressed, the PTI manual, you're going to see that these beams, they come like a structural steel section. You have section properties. You're going to have A, you're going to have C, you're going to have R squared, you're going to have S top, S bottom, Y top, Y bottom. You're going to have all of these values. They can just give it to you. You don't really need to calculate the moment of inertia for this section. I'm going to say maybe for a T section, like ours, that we are using here in this homework, yeah, it makes sense. It's going to be simple, just a flange and a web. If there's more than this, I'm not going to do it by hand. I'm not going to do this little triangle top and bottom. And I mean, this is going to be too much. So be sure that in your spreadsheet, you have a chance to input CT, R squared, and AC as a numerical value, if you like. When you do this, you need to be careful because at the beginning, when you apply the pre-stress force, you're going to have here some tension like what we discussed. We said in this side's going to be compression, this side's going to be tension. So let's say at the initial, as we said, you're going to have your compression. This side also is compression. This side is tension. You're going to end up with some tension at the top. You know that in some cases, we don't add non-pre-stressed reinforcing in the top. And if the stress here is high, your beam is going to crack. So you need to limit the tensile stress in the top and also the compressive stress in the top. You need to have certain limits. You cannot just apply any tensile stresses on the top of the beam or bottom of the beam. You got to be careful on what you'd like to achieve. There's a method that's called here C-line method. This method, you don't really need to use it. You don't have to use it unless it's going to be mentioned in the problem, but it has some physical meaning. It's going to explain to you, once you look at it, you're going to say, now I understand how the pre-stress system works, or what mechanism we're talking about. And with this method, we're going to be doing the exact same thing that you're doing here, finding out stress top and bottom at the initial, at the time of transfer, and at the service level. But it's going to be slightly different. I say, okay, let's look at it. This is here a comparison between conventional reinforced concrete beam and between pre-stressed beams. How does it work? Case A here, when you have no load. So I'm going to be zooming in and say what happened here in case A. No loads. If you have no loads, would you have any tension compression in the steel, in the beam, in the concrete beam? I'm going to say no. The tension force in the steel is going to be nothing because you don't have any applied load. Where is the tension going to come from? Don't forget, we're doing here serviceability analysis. We're doing check on the stresses. We're doing force analysis. We're not doing capacity. So someone's going to say it's going to be equal to yield times cross-section area. I'm going to say, yeah, this is true, but this when you find the capacity, which means when it is loaded. But at this initial case, if there is no load, there is no tension, no compression, because the external moment will need to be equal to the internal moment in this case. How much is external moment when you have simply supported beam? I'm going to say W squared divided by 8. How about the internal moment? I'm going to say C or T multiplied by A, which is the arm between the tension to compression. And here, I'm going to apply some load. Look what's going to happen. I'm going to have here some tension, some compression, and of course, they're going to be equal to each other. And applied external moment here is going to be equal to C or T multiplied by A. I'm going to apply here more load, higher load. What's going to happen? This value here, or this force, is going to get a little bit higher. And this arm is going to get slightly larger till I reach the capacity point. So usually the moment, external applied moment, W squared divided by 8 for whatever load that is going to be given to you, is going to be equal to C or T multiplied by A. So this is a way that we have in conventional concrete. In pre-stress, it's gonna be different. Let's look here at pre-stress. When you start, you have no load, but you're gonna have this pre-stress force. The stresses is not gonna be equal here to 0. And the amount of compression and tension force, they're gonna be aligned with each other because there is no external moment. Now, if you have no external moment, and then you're gonna say external moment is gonna be equal to the internal moment, like what we have done here. Let me put this back here. I'd like to write this down. I'm gonna say M external is gonna be equal to M. I'm gonna say sub external is gonna be equal to M internal. What's the external moment? WL squared divided by 8. What's the internal moment? It's gonna be equal to C or T multiplied by A. They're equal to each other. So once you start to have some external moment, you're gonna start to develop some compression force and tension force. But here it's different. If I'd like to apply the same principle, I'm gonna say, yeah, let's try that. External moment is equal to what in this case? It's gonna be equal to 0 at the beginning, right? But how about this pressure? Do you still have some compression force? Yes, you have this compression force. Therefore, A is gonna be equal to 0. Otherwise, the system is not balanced. Once you start to apply some external moment, you're gonna start to build some internal moment. This tension or compression force is gonna be the same because the amount of pre-stress is not changing. But what you're changing is gonna be the location of this force. You're gonna be pushing it up. Which force? The compression force. Because the tension force in the steel is giving the same location. Look what happened here. Now we start to push this up. We start to push this up. This force, the compression force, we start to push it up. We start by having it right here. Now we start to push it up. So that the external moment is going to be equal to the same thing. It's going to be equal to the internal moment. And in this case, P or C or T times A is going to be equal to this W1 L squared divided by A. Now what happens when you apply more load? You apply more load here, this compression force is going to start to move up and up. It's going to move like this. Now, your internal moment is going to be equal to the tension or compression multiplied by A. And A in this case is going to be equal to E plus E prime. What is E? The amount of eccentricity that you have there. What is E prime? It's going to be the distance from the centroid to the compression force. So, okay, good. All right, now I guess we understand what's happening here. We understand the principles of it, but we don't know how to find out the stresses based on these forces. Okay. Here is general case. When you have the tension compression, which is a pre-stressing force, and this gonna be A, the moment arm, and this gonna be your eccentricity, right? This gonna be E, and this E prime, which is equal to A minus E. E is gonna be a given value to you. You can figure it out, or you can decide on it, or given to you. This moment is gonna be equal to C times A or T times A, right? We have here a couple. This E prime, as I said, is going to be equal to A minus E, but E is going to be one of these constant values going to be given to you. Now let's look here at the top stresses. This top stresses is going to be equal to this compression or tension force divided by AC. And then you have the other component coming from this compression force times E prime multiplied by C top divided by IC. What is this? I'm just wondering. If I'd like to take this, what do you call this? Call this S top, correct? This give you your S top value. And C times E prime is going to be an additional moment in the top of C divided by A. It is not going to be the total moment because the total moment equals C times A. Now this is going to be C times E prime only, which means a moment about the centroid. If I take here this line, it's going to be this C times E prime. So this is not the total moment. This is going to be the moment about the centroid. So this moment about the centroid divided by the section modulus in the top and same thing at the bottom. If you do it with this method, with this C-line method, or you do it with the basic concept method, you need to end up with exactly the same stresses. Any questions? Yes? No?
I think we're good.
Right. Now, someone may ask a question here and say, where is the effect of dead load? Where is the effect of live load? Where is the superimposed load? Why did you just consider this compression force and you just disregarded all of these values? In here, it makes sense when I start to say dead load, total load, right? Are they into this? I mean, are they into this equation considered? You can say yes. They're into this equation. Because think about it this way. If you just take this compression force divided by A, and then you take the tension force, which is a pre-stressing, times only E, what's going to happen? Just times only E. You're going to be doing it like here, like in this case. Correct?
Yeah.
And then you're going to be adding little load. And this little load is going to be pushing this force, the C force, from here, from the bottom. You remember we started with the force right here. You're going to be pushing it to here. So if you add the load, which is the same as this tension force, and you bring it all the way to the middle, right? You're going to end up with some external moment exactly equal to the internal moment that you are developed by the pre-stressing. Now you have internal moment due to pre-stressing. If I may go back here, and this internal moment due to pre-stress is going to be pi over AC multiplied by this. Don't forget, I have here three components. The first component is going to be the axial compression, right? Effect. Second component, which is this pi over AC multiplied by EC, this is going to be the moment due to the eccentricity. And then the third one is going to be the external load effect. If I put a moment which is equal to exactly pi times E, what's going to happen? If this moment here, if I just assume for a second that this M dead load equals pi times E, what's going to happen? How much stress would you end up with? Can someone help me with this? If I put this M dead load to be the same as the effect of this, what's going to happen?
It's gonna go to 0.
Yeah, which 0? This part here, this effect of the external applied moment is going to get canceled with this. It's going to cancel with this. You're going to end up with only compression force in the concrete. You're going to have uniform stress in the concrete. Does this make sense?
Yep.
Okay, let me take you to another stress distribution equation. Yeah, say, let me look at this. So, okay, this one here represents the axial compression, and this one here represents what? The eccentricity of the cable, right? And this one here represents, this last term, the external force. If I put this external force, which in this case is M dead load, right, in the other equation, if I put it equals to P times E, what's going to happen? If this value here, M, equals P times E, this is not P, this is P times E, what's going to happen? This term is going to cancel with this term, right? And you end up with P over AC. Meaning, if you consider just the force divided by the cross-section area, as if you have put a moment that's going to be balancing the effect of the pre-stress. You guys like the statement? Or no? Let me repeat this again. If I'm going to put here enough moment or enough load, and this moment that I put there is going to be equals to P times E, which means it's going to be equivalent to the effect of the eccentricity of the pre-stress. It means I'm going to be counteracting the effect of this eccentricity. I'm just canceling it out. And once you cancel it out, the stress top and bottom is going to be equal to P over AC, because guess what? This also negative, it's gonna be positive. So this 2 also is gonna get canceled. And you end up with a stress of P over A as a compression only. So if you did not provide any load, you're gonna have combined stresses from the axial force and the eccentricity, which is this one here, right? But if I put some moment, which is only enough to balance the effect of this eccentricity, to cancel it, I'm gonna say to balance it, to balance this eccentricity, I'm gonna end up with a stress very similar to this, only compression throughout the entire depth of the beam.
That's kind of what we want to do, right?
Yeah, exactly.
So there's no cracking at all.
You are not gonna have any crack if you just put the balanced load, right? But this is not gonna be the design load. I'll tell you the reason. But this is gonna be like one of the goals is to be close there. So what happened? This C over A means what? This C over A means that your applied load is gonna be causing a compression force right at this level. And in that case, right, in this case here, when the force is gonna be right here, it means that you apply enough load to balance or to counteract the effect of the eccentricity of the cable. So when you do C over A, it means that you consider some of the dead load and life load that you consider there, right? That I consider in the other method. So this C over A, it includes the effect of the balanced load. What is the balanced load now? The balanced load is going to be that load that you put on the top of the beam to counteract exactly the effect of this eccentricity. Now, this additional E prime that you multiply by here, this accounts for the remainder of the load. Because you know when you have the total load, right? What's the total load? Dead load, superimposed dead load, and life load. If you take a part of it, like fraction of it, we're gonna quote here the balanced load, right? It's gonna be equal to T times E. This is gonna be the moment developed by it, right? And this additional is gonna be for the difference between the total load and the balanced load. Kind of confusing. And just pass it for now. And then we're gonna come back to it. We're gonna redo it. So in here, this is gonna be like the general equation, if you like, just as conceptual. And this one here, if you like to check the service case, so it's gonna be PE, PE, and in this case, use here AC. And also, if you like, you can rewrite this equation. You see this I and C, and you can write it this way, like what we have done in the past. You remember this equation? We start by equation like this, and then we change it to this fashion. You guys remember this? You see the PE over AC, I'd like to take A out, so P over AC is gonna be taken out, and then it's gonna be 1 plus E times CT divided by R squared. Just rewrite this equation, right? Very similar to what I have done here. If I may take you back, how did I come up to this equation? I start with this equation here, right? And then I start to change it, if you recall this process. I guess now it's gonna be the time that we open the new slide set. Now let's talk about this load balancing that I just mentioned to you. Our goal here is to try to balance some load. So actually, when we apply the pre-stress on this cable, we're pushing this up. We're pushing the entire beam up. So we're pushing the beam. We're applying loads from the underside of the beam going up. This is gonna be the direction of our loading when you just do the pre-stressing. And your goal is to balance it with this applied load. If this load is exactly equal to that load, it means that you're gonna be right at the balance point. At this balance point, what's gonna happen? The moment coming from the top, or the load coming from the top, is gonna be exactly equal to the moment coming from the bottom. This is exactly it. Let's try to figure out here how much is the load coming from the bottom, right? You see what I said? Load coming from the top, you can figure it out. You can say it's gonna be the weight. I know the load. It's gonna be dead load, superimposed dead load, it's gonna be live load. I guess I can determine this. How do you do it? You do tributary area, load criteria, and then you figure out the amount of load from the top. So this one is going to be given. This is like based on the design criteria. The question is, how much load would you develop here, or would you bring up here to balance this load? So I said, well, let me do some analysis on this. Here's the profile of the cable. Beginning, the end. You apply a point load coming like this horizontal force. But in reality, it's not like this. You guys know this. In reality, the force is going to be coming like in an angle. So I'm going to say this is going to be the horizontal component of this force, right? I'm going to take this out for now. Excuse me. I'm going to start by putting the coordinates x and y right here at this point, at the low point. The equation for this parabolic shape is going to be like this. Ax squared plus bx plus c is going to be equal to y. Now, where is y? Y is going to be this component. So at any point here, this is going to be your y distance, right? And where's the x distance? It's going to be from here to there. It's going to be the x, this is going to be the y to that point. Now I need to figure out these constants, a, b, and c. When x and y equal to 0, how much was the y value? I mean, x and y is going to be equal to 0. What's going to happen? X and y is going to be equal to 0. How this going to help you? You're going to say, put x here equals 0. This is going to be 0. Y is going to be equal to 0. Therefore, c equals 0. Correct? Once you set up x is going to be 0. Y is going to be 0. 0, 0 plus c equals 0. Therefore, c is going to be equal to 0. So I'm done with this variable c because I picked the point to be right here. If you pick the 0 and 0 point to be right here, your c value is going to be there. It's going to be present in this equation. But in this case, I picked it to be right there. Also at this point, what's going to happen? The slope of this line, of this curve here, is going to be flat, which means the slope is going to be equal to 0. Which means first derivative of y to x, partial y by partial x, is going to be equal to 0 at that point. What's the first derivative of this equation? It's going to be x squared plus b, right? Of course, you're going to take the 2 and drop it down here. So it's going to be 2ax plus b. Now use x is going to be 0, and y is going to be 0, and also the slope is going to be 0. So this point is going to be 0, and this x is going to be 0. You end up with also b is going to be equal to 0. So my equation I'm going to end up with is going to be ax squared is going to be equal to y. I said, how about a? How can I find out the a value? You say, well, I guess by using this point, I was able to solve for b and c. Now at this point, I can solve for a. How is that? When x is equal to L over 2, y is going to be equal to a. You see this a lowercase. Okay, here's my equation. I end up with ax squared equals to y. I said when x equals to L over 2, y is going to be equal to a. I guess I can use this x and y in this equation and solve for a. Here's the a value, 4a divided by L squared. Now this becomes my equation. So for this profile, my equation becomes 4a x squared over L squared. Second degree parabola. Good. How about the load? You can see here from calculus and from, I'm going to say, elasticity principles, I know that the uniform load is going to be equal to P multiplied by the second derivative of this curve. Now, what's the second derivative? I mean, here's the equation. You're going to differentiate this twice. So the first time is going to be 2 times 4 is going to be 8al squared. Second time is going to be what? 8al squared. Second derivative. So let me look at this. Differentiate it twice, right? P times, this is going to be W. So W equals 8PA divided by L squared. Okay, now I have it. PA equals, I can rewrite this, it's going to be W squared divided by 8. What do you call this for the given load? What's the name of this? It's going to be the external moment, right?
Moment.
Yeah. How about this one here? P times A, what is that? Internal moment. How's that? Look at this. P times A is going to give you the internal moment because it's going to be two forces. You have tension here, compression there, right? So P times A is going to be equal to W squared over 8. So someone's going to say, now this makes sense. This like more physical meaning to it. But this one here is kind of just mathematical. I'm going to say derivation. If you like to drive here, the constants A, B, and C and find out W in terms of P. But this one here, it makes more sense to think about internal moment is going to be equal to the external moment. So you say, okay, this is nice. Which means if I know the amount of force that I put there, I can figure out the balanced load. What's the balanced load? Balanced load is going to be the amount of load that you are pushing with it up, so that when you put new load on the top, right, is going to be equal to each other. They're going to be exactly equal to each other. Okay, this makes sense. You give me this amount of force P, right, based on this equation, just the horizontal component, right? I can figure out W, how much load we can balance with this pre-stress force. Or if I give you W and they say, try to balance exactly this load, what do? You say P is going to be equal to balance this load, the load that you like to balance, that you ask me to balance, multiplied by L squared divided by 8A. With that, I have this much tension force. Any questions, or I'm moving fast?
Professor, is internal moment always equals to external moment?
Yes.
In any case?
If always in any beam, any material, if they're not equal to each other, beam is going to collapse.
Right.
Right, absolutely. So what happened here again, if I give you a certain load, I'm going to say, try to balance, let's say 2 kip per foot. The span is going to be this much. So I need your help with this. Let's do it together. I'm going to say, we're trying to balance here. Balance 2 kip per foot. Span equals 30 feet. A equals 6 inches. How much force should I use? I need your help. Yes. I'm trying to balance here 2 kip per foot.
37.5.
The span, L, yeah,
I got 30.
and 30 feet.
37.5.
A, I'm gonna say is equal to how much is A? I'm gonna say half a foot, right? I can
got 3.
external moment is gonna be W times L divided by 8. If I take this divide by A, give me the amount of force. Is this what you're getting, or
Professor, I think A is, oh yeah, it's half a feet. You're correct.
if
We,
you
we didn't convert it to the feet.
yeah, look at
That's
this.
why.
This is what you have done. You put it 6 feet. Look at the value. This is what you guys are getting, right? You need to put as half a foot. Units is going to be very critical. And just so you guys know, usually units in pre-stress is going to be in PSI or KSI. Keep this in mind. So let me type it here. PSI or KSI only. Don't do like kip per square foot. Only kip per square foot and pound per square foot is used for foundation design. Not for concrete analysis or steel analysis, wood analysis. We don't do that, right? So I said here, in this case, I'm gonna have here 450 kips. So what does it mean by that? It means if you bring a beam and you put eccentricity of 6 inches and you put a compression force of 450 kips, you're gonna be balancing 2 kip per foot. Whatever moment that this 2 kip per foot is gonna be bring you the beam down, this is gonna bring it up. What does it mean in this case? How much deflection would you have, you think? What beam deflection?
No beam deflection, right? 0?
Nothing, 0. Because deflection is going to happen from the applied moment, right? Now the top moment, applied moment, is going to be exactly equal to the internal moment. They are going to be balancing each other out. So you don't have any deflection. Now your beam is going to be flat. Meaning, at the beginning, when you apply this force and no loads applied to it, the beam is going to go up. It's going to camber up, right? It's going to be going up because you have this force applied to it. This R is going to be there. It's going to bring it up. Now, once you put this external force, the 2 kPa is going to bring it flat. I said, okay. Here is the load. And this is the same equation. We're just going to be rewriting it, cleaning it out a little bit, and put W in terms of P and L and A. And again, be careful with units. Now, don't forget that the actual force is going to be in this direction here. It has an angle, meaning you have vertical component, horizontal component. The one that we use here, don't forget, this is going to be the horizontal component, right? Vertical component needs to be considered. Now, if you do some analysis, just, this analysis here, this few slides, this is if you're going to be taking the point of 0 and 0 right here. So you're going to have like an A and C factor, right? So I'm going to skip this for quick because this is exactly what we have discussed, right? And if you want to look at this component here, the vertical component is going to be equal to that value. If you just take this, right, and then you have the slope of this line, and then you figure out this component is going to be equal to 4 PE over L. You say, yeah, it makes sense. Do you know why it makes sense? Let me show you this. Your load that you're balancing is going to be equal to 8 PA over L squared, right? Remember this, 8 PA over L squared. I'm going to take you to here. If this load equals this R, I'm going to say R, which is the same as this balanced load, is equal 8 PA, right, over L squared, right? If you take this load multiplied by the total span, you're going to end up with what? 8 PA over L. Am I correct? Only over 1 L. Yes or no? Multiply by the span. Take this load. This load is equal to 8 PA over L squared. I'm going to take the entire load, multiply by L. So I'm going to be losing L squared, correct? And then divide this by 2. Why? Because you're going to have here 2 reactions. So this is going to be 4. 4 PA over L. This is by static principles. Here we go. Look at this. 4 PE or A, right? The eccentricity divided by L. Let me repeat this again. I'm going to say your W equals 8 P times E or A divided by L squared. Your reaction at one side is going to be equal to W times L divided by 2. Therefore, this R equals, take this W, multiply by L, you're going to be losing one of these L's, and also divide by 2 is going to be 4 P E divided by L. Does this make sense? Yes or no? Bottom line is you really need to have this component. Otherwise, the system is going to be unstable. When you have load coming from the top, reaction is going to be going up, correct? Because you're going to have compression. Now, in pre-stress, what's going to happen? The beam wants to lift up because this reaction is going to be in the opposite direction. The reaction is going to be coming downwards. So the reaction due to dead load is going to be going upward. The reaction due to pre-stress is going to be coming down, which means the beam wants to lift up from its place. Exactly what you have. Look at this WP. We're going to quote here the balanced load, right? Or W due to this force P. It's going to be equal to 8 PE over L squared. It's going to be going up, and the reaction is going to be coming down. This method we call load balancing method. We have here some information if you like to look at this pre-stressing, and you just have a straight line. You're going to have equivalent moment or load is going to be equal to P times E, right? This is the one that we're using, right? This W, it depends on the profile of the cable. So here, based on this profile in the cable, is going to be 8P over L squared. This is what we keep on using, right? If you have it hard like this, it's going to be 4P over L, which means external moment divided by the span, if you like. Now, let's see what's going to happen in this load balancing method, which is very similar to the C line, if you like. Right at the balance point, if you guys recall, at the beginning, when we start before loading, the tension was exactly the same. It was aligned with the compression force. So tension was aligned with the compression. And the stress is going to be equal to the dual effect of the pre-stress force and the eccentricity. So we're going to say I have P and moment. Once you apply this load, W balance, to be exactly equal to the balanced load, which is the reaction that's coming from here, from the cable, this force is going to be moving right here to the centroid. And therefore, the effect of this eccentricity is going to be canceled out by the effect of this balanced load. And the stress in this case, if you look here at the stress now distribution, the stress in this case is going to be equal to P over A. This is going to be like the compression side. The red line is going to be the datum. And this one here is going to be MC over I coming from the pre-stressing. And this one here is going to be coming from the balanced load. But it's going to be opposite to it. So when you look at the stress on the top, it's going to be this compression. And then you add some compression to it. And then you add an equivalent tension to this compression. You end up with only P over A because both of these two, they're going to cancel each other out. So what happened in the balanced load? Right at the balanced load, the eccentricity is going to get canceled by the effect of the balanced load. Any questions? I'm sure that you guys have questions. Is anyone there?
Yeah, we're just like slowly taking it in and reading the slides.
Should I go back to any slide and repeat, or we're good?
I think we're good.
Can move on?
I think we're good.
Okay, so just confirm again. We're going to have external moment and internal moment. When they're equal to each other, we're going to be at the balance point. What does it mean by equal to each other? It means this moment here, due to the eccentricity, which is the first moment, is going to be exactly the same as the moment due to the balanced load. And in a case like this, the stress due to the eccentricity is going to cancel out with the effect of this applied balanced moment. And in that case, the only pressure is going to be having through the beam or stress is going to be only P over A. So, okay, good. So after you apply, so I'm going to say, okay, it's going to be only P over A. I understand that. So the question is, if I'm going to put load higher than the balanced moment, what's going to happen? Let me put some numbers. I'm going to throw some number there. Yes, say my balanced load, like in the previous example, the one that you have done is going to be 2 kg per foot, right? It's going to be W balanced. But you know what? I decided to add more load. My total load, I'm going to say here W total, which is equals to W dead plus superimposed dead plus live. I'm going to say this is equal to 3 kg per foot. Okay? Just for sake of discussion, I'm going to throw these numbers here. Your total load is 3 kg per foot. Your balanced load is only 2 kg per foot. How much is unbalanced load?
Is it 1?
Yeah, how much you're unbalancing, or how much you don't really balance. I'm going to say 3 minus 2 is going to be equal to 1 kb per foot. This additional load, this was going to be causing a stress very similar to this. And this is what you can add now at that point. So you say, okay, let me look. If top and bottom, if you have this unbalanced load, if you can figure it out, like very similar to what I have done here, and then find out the moment for the unbalanced load, the stress at the end is going to be equal to P over A plus or minus M unbalanced divided by S top or M unbalanced divided by S bottom. And this analysis is going to give me exactly the same values that you would get if you like to use this method. Exactly same numbers because it has the same meaning. So what I'm doing here, I'm taking the moment, this moment, and divide it into two components. So I'm going to say here M total is going to be equal to M balanced plus M unbalanced. The first term, which is this imbalanced, is going to be canceling the effect of this. It's going to be taking this out, correct? I understand that imbalance is going to be canceling the effect of the eccentricity. Meaning, at the end of the day, I'm going to have P over A, and then I'm going to see here minus M unbalanced, because imbalanced was used against this. M unbalanced divided by S top, which is right here. Same thing for the bottom. Meaning that this P over A is going to be the stress at the balanced load. So if someone's going to be asking you, how much is the stress at the balanced load? Do I need to prove to him that the applied moment is going to be equal to the pre-stressing moment, and therefore they're going to be canceling each other out? I'm going to say no. At the balanced point, the stress top and bottom is going to be equal to P over A. That's it. Done. If you like here to look at the total moment effect, in this case, this equation, this is going to be PE for the effect of pre-stress, and this is going to be the M unbalanced, which is equal to the M total subtracting imbalance. How's that? Very similar to what I'm saying here. W unbalanced is going to be equal to W total, 3 subtracting 2, which is W balanced. Example. This example now is going to make our life much easier because it's going to show all the numbers and it's going to be like real problem. Ready for this example?
Yeah.
You need a couple of minutes break or 5 minutes or no? Just continue. Just hit the example. Which one?
I'm ready.
What?
I'm ready.
Ready. Right. Very good. We have pre-tension member. It's a beam. It is double T. Here's the way it looks. Here's a cross section. This is what we call here the span, 64 feet. And once you look at this section, you're going to say, now, who's going to do the moment of inertia for this? Who's going to do the cross-section area for it? I'm going to say, you know what? It's going to be all given to you. You don't have to worry about it. Load for superimposed and live load is going to be 420. How about the self-weight? Let me go back here. Here's the span, 64 feet. Superimposed and live load is 420. And then they say initial pre-stress is going to be FPI. This is the stress. FPI, not PI, is going to be equal to this much, 189. Look at this. The conventional rebars that we use, it has yield of 60 KSI. Look at this one. You're going to put pressure up to 189 KSI. The effective after losses is going to be 150. And then it says here, figure out the stress top and bottom at the initial full pre-stress, no external gravity load, and the initial service load, right? Excuse me, the final service load. This is after you apply dead load and live load and the whole thing. Let me see what information is available to me. And also I need to understand this pre-stressing cable. Again, they give me the cross section. They give me the drape of this cable, and they give me the total load superimposed on live load. And here's the available concrete properties. They say concrete is going to be 6,000 concrete, lightweight. Maximum allowable compressive stress at surface is going to be 45% of this F prime C. So when do you think this F prime C is going to be attained? Is this after a week or after 2 days or when? At 28 days, right? They specify the strength. There's another factor here, or a strength, which is this F prime CI. What is F prime CI? This is the strength at the time when you do the initial pre-stress. You know, after 2-3 days, we're going to be taking cylinders and measure the concrete strength. And once it reaches 4,800 psi, we can do now the pre-stress. So you don't just do it when the concrete is still fresh. You need to wait, and once the concrete is going to be reaching this F prime C, you're going to do the pre-stress. So it's going to be 3 to 4 days. So at the time of pre-stressing, when you transfer the force to the beam, the stress in the concrete or the strength is going to be 4,800 psi. The allowed at the surface level is going to be 45% of F prime C, which is 45% of this, 2,700 psi. But the allowed at the time of transfer is going to be slightly higher. Look at this. It's going to be 60% of this value. It's going to be 2,880 psi. But this is not going to stay forever, right? Because what's going to happen, the pre-stress force itself is going to reduce because you're going to see here some losses. Look at, this is the reason that this is going to be 6%, but eventually when you start to use it, it's going to be 45%. So this stress is not going to stay there. The actual stress is not going to stay there for a long time because loss is going to start to happen. How about for the steel? What steel are you talking about? The steel, I'm going to show you now the numbers, going to be 416. I'm going to show you exactly the properties of it. The highest stress, which is the tensile strength of the tendon, of the rebar or cables, is going to be 270 KSI. Now compared to the regular steel, right? Conventional steel is going to be 6 KSI. It is supposed to start yielding at 220. So this is the maximum. This is going to be the yield. And the initial pre-stress is going to be 70% of this FPU. It's going to be 189. Eventually, the stress is going to drop down at the service time to 150 after you have here 20% of losses. So again, we're doing here 2 checks. One of them is going to be at the time of transfer, which means at that time, the stress is going to be equal to, at the time of transfer, is going to be 189 KSI. And the other one is going to be at the service level, which means after you apply all the loads, it's going to be 150 KSI. Are we good?
Yes.
All right, great. Let's look at the available cables and wires. The cables we're using is going to be this 416, ASTM 416, right? And we're going to be using this 7-wire strain. That's why I made it here and highlighted a little bit. This is the reason that says here 270, which means this cable here, right? Look at the available cable size. It says here 3/8 of an inch, 7/16, half an inch, which is very common, and 0.6. So most likely we're going to be using this guy, half an inch. Cross-section area is going to be 0.153. If you notice here, this cross-section area is much smaller than regular conventional reinforcing of half an inch. For half an inch conventional reinforcing, which is number 4, you're going to end up with 0.2. This is going to be only 0.15. So the cross-section area is going to be smaller, right? It's going to be 0.153. You cannot do pi d square over 4. You cannot do any of that. You just look it up from here, right? More information about our double T, about the beam. It says, assume that you have 10 half inch diameter, 7 wire strand tendons. I'm wondering, what is this? 108D1. This is like the section call out. Like, for example, in steel, you say W16 by 31. It's going to be very similar to it. And then they give you here all the parameters. They give you the cross-section area. You don't need to calculate out. They give you moment of inertia. They give you R squared. You know, for our equation, this R squared is going to be given to you. C top or Y top, C bottom and C top, you have it. And the eccentricity between what? Between the centroid and the bottom of the cable at the drape or the heart. And then you have S bottom, S top. And also the self weight of the beam is given to you, 359. So everything you have is going to be right here. If you look here for the loading is going to be this dead load 359 P left plus you have superimposed plus live load of 420. So you have total of 420 plus the 359. All right, we're good. Any questions? Any missing information? RJ, are you there? Bassem?
No questions.
No questions.
All
No
right.
questions.
So far.
Thank you.
Yeah.
Thank you. All right. Let's figure out here, at the time of pre-stress, we said that the stress is going to be equal to how much? PI. Let me take you back here. 189 effectively is going to be 150. Cross-section area, I have 10 strands, half inch. Cross-section area, 0.153. So I say, okay, here is APS. What is APS? This is going to be for the pre-stressing. AS, conventional rebar, cross-section area. APS is going to be for the pre-stressing. 10 times 0.153, cross-section area for 1 half inch 7 wire strand, 1.53. The amount of force PI is going to be equal to this cross-section area multiplied by 189 KSI. Here we go, 289 kips. How about effectively? Later on, it's going to drop from 189 stress to 150. It's going to be 229.5 kips. So, okay, now I have the force P. You remember the equation that we used? Let me put it back so that you know what our target is going to be. Here's the equation. So I need PI and I need PE. So I have here two cases. I have the first case at the time of transfer, and then I have another case at the service. I need PI and PE. I guess I need also AC, E, CB, and R squared, which I have all of that. And also I have this as bottom. Don't we have it? Yeah. If I go back here to our slides, I'm going to say that I have all of this information. Right? I have A, I, R squared, CB, C top, S bottom, and S top. I have all of this information. Okay. How much is this moment due to dead load? You say dead load is, look here, 359 P left. 359 times 64 squared divided by 8 and then multiply this by 12. Why should I multiply this by 12? Just wondering, if I take this is gonna be what? 359 what?
Feet. Or no, inches.
This is what? 359 pound per foot. This is gonna be foot squared divided by 8. W squared divided by 8. Why do you multiply by 12? To get
Per
it in
feet.
pound inch.
To convert.
Yeah, because you'd like to put it in pound inch. Because
Per
later
inch, I
on,
mean.
yeah, you need to be very careful now with units. You remember this issue? We were just doing a very simple analysis for a beam, and I said eccentricity is going to be equal to 6 inches, and everybody used 6 inches in the analysis, right? So you get to be very careful. You do it as in foot, or if you like, you do everything is going to be in pound inch. My recommendation, do everything is going to be in pound inch, right? Just do it in pound inch here. Numbers going to be slightly large, but at the end, it's going to be perfect when it comes to analysis. You don't want to be confused. You don't want to get weird numbers. So do everything in pound and inch. Here's half inch again. Little bit more information about this. 0.153 cross-section area. And this is a nice table because it tells you here, at the time of transfer, you see this 0.7 FPU for 270 is going to be this much. It's going to be this much of a force for each strain. If you like to use it, you can go ahead and use it. But I would just use the analysis here because don't forget, your goal is to do a spreadsheet with this. So use the cross-section area for one strain is going to be 1.153. And the amount of tension that you're going to have there initially is going to be 189 KSI. Finally, it's going to be 150 KSI. So you need to be ready to do all of this analysis quick in your spreadsheet. We're going to be using this, I'm going to say here many times. You don't want to do all of this by hand. It's going to be too much work. Now, you guys have seen this. Look at this example here. I mean, here's the equation, right? So I'm just going to be using it. Here's the equation. It's true, slide set 3, but maybe the slide number is not exactly. It's going to be slide now number 46. If you like, this is going to be 46. So here's my equation for the top stress. And I'm going to have also another one for the bottom stress. Say F top. Do you have this pre-stress, initial pre-stress? You can say, yeah, this is going to be the 289. Let me look here, 289. You have the cross-section area, given. You have E, the 1477. Also, that was given. It's right here. You see this? So I'm going to have all of these values given to me. R squared, C top, M dead load, which is right here. Here's the M dead load, right? It's going to be in pound and inch. Divide by S top. Look at this. I'm following all the signs, right? Very careful about this. Very careful about units. You end up with negative 70 psi compression. You can make your life much easier if you do a spreadsheet. If you like to try this by hand and just have fun, and most likely you're going to do a mistake, right? If you use a calculator, you're going to have some computational error. This is very standard. So you don't want to do this. And you don't want to be overwhelmed with the stresses and this calculation. So try to use a spreadsheet from now and test it.
So Professor, all the parameters will be given. For example, like for an exam, you just have to.
Yeah, all of these parameters. Yes, absolutely. I mean, how would you figure this out? Unless I give you a simple section. What do I mean by simple section? Rectangular section, right?
Right.
Or a very simple T section and give you some information.
That's really good. Thank you.
Yeah. You cannot figure out the moment of inertia for this. I mean, it doesn't make any sense. This is not a statics class. I'm not trying to find out the centroid moment of inertia. I mean, you guys, you should know it and do it for simple shapes. But when it comes to this complex shapes, I'm just gonna give it to you, like in here. And just, you know, in the PTI manual, you can see all of these sections. They are available, like the steel book, you know. So you don't want, you like to understand what you're doing. And when it comes to calculation and simple calculations, I don't want you to get stuck here. Because you can spend time trying to figure this out and you're not getting the same answer. But if you have your spreadsheet, you put the dead load, you put the S top, S bottom, you put all of these variables, and right away you're going to have the answer for the stresses, right? So now you're going to concentrate on other stuff. It is not really about this using the calculator thing. I don't want you to spend time there. So we did here the top stress, and we did also the bottom stress. I'm just going to fly here because I'm going to say, you know what? You have PI, you have area. It's going to be exactly the same equation, but different signs, right? And here we go. Now you ended up with this much compression. So I'm going to say here at the time of transfer, I have compression on the top of 70 psi, at the bottom of 22, 27 psi. Compression, bottom is going to be compression. Is this allowed? I'm going to say, okay, let me take you back to confirm this value, right? Let me take you back and see what is allowed. Here's the allowed stress. It says here at the time of transfer is going to be 2880 psi, 2880 psi. I said, okay, 6% of this. I said, okay. Did we go beyond this limit? 70 compression, no. Did we go beyond this limit? I'm going to say, no, we're good. So this is great. I mean, this amount of force that we put in there on this given section. So I'm going to say for this given section here, and the amount of pre-stress that you put there, 10 strands, 5 here and 5 there, right? They need to be equal. I cannot put here 4 and put here 6, right? They need to be equal. Otherwise, you're going to be twisting the double T. So in this case, once I applied here, I put 10 strands, I put to tension, to PI, I'm okay with the stresses, the beam or the double T is not collapsing because the stress is still within the limits. I have certain limits, I need to keep the beam with it. So top and bottom, at the initial pre-stress, I have no problem. Let's see what's gonna happen eventually, right? I'm gonna say at the final condition at service load. I'm gonna say what's gonna happen at the service load. I'm gonna be adding this dead load, superimposed dead load on live load. Previously, that was given to me as 420. This is slide 30. I'm gonna go back here quick. Yeah, look here at the beam. It says here 420 for this superimposed NW live load. I said, okay, it's gonna be 420. How about the moment? I'm gonna say multiply by 64 squared for the span divided by 8, multiply by 12, put it in pound inch. I guess we learned this trick about units. The total moment, now take the dead load moment from the previous slide, plus this superimposed and live load. Now this is gonna be your total moment. Your total moment about 4.7, right? Million pound inch. So okay, good. Now this is gonna be your total moment. Now let's look here at the stresses when at the time of service level. Now I'm gonna have here PE, not PI. If someone wants to check this out, 229,550, I'm gonna go back here. Here we go. 229,500. This is gonna be your PE that you just calculated out. Divide by A. All of the factors gonna be the same. Now 4.7 million pound is gonna be your total moment. Check the stresses. What do you have? 898 psi compression. What is your limit at the service level? Is it 2880? You see, here's the limit at the time of transfer, 2880. But look at this again, the limit. Limit is 2700, which means 45% of this F prime C. So the limit at the time of transfer is going to be different from the limit at the service level. Just keep this in mind. Now check the stress here, less than 2700. This is good. Now check it also at the bottom. Same equation that you guys have. Now this becomes like a very simple spreadsheet again. It's going to be 930. Or what do you have? 594 psi as intention. And then they say, be careful because you cannot go beyond this 12 square root of A prime C. So you're good. This beam is good. With this design loads and with the amount of pre-stress strands that we put there, this beam is okay. Now someone's gonna say, does it mean that you allow tension on the bottom of the beam? I'm gonna say yes, you allow tension on the bottom of the beam. It depends on the performance that you're looking for. Do you want the beam to crack or you don't want it to crack? You can decide on this. If you don't your beam not to crack, you better be sure that you don't have any tensile stresses at the bottom. Otherwise, you're going to be building some cracks. And you can end up by having some compression stresses at the end, at the bottom. But here, we allow some tension. But the maximum is going to be 12 square root of A prime C. Later on, I'm going to show you the code and what does it say and what you can allow and what you cannot allow. It depends on the criteria that, or the performance criteria that you'd like to pick and choose. I said, great. So what method did I use here? I use this method, the basic concept method, meaning I just use this two examples. I say, great. Just find out the stresses and compare it with some allowable stresses, which is great. I said, I'd like to solve the previous example, but I'm gonna use here two other methods. How many methods do we have? Just to remind you, I have the basic concept with these two equations. I have the C-line method, which is this one here. Do you remember this? C-line method. And also I have at the beginning of this lecture, I have something that we call balanced load method. You remember this method here, the balanced load? We have done this, right? Let's give you the balanced load method. We can use also this method. So, any questions?
So out of those three methods, I mean, is there like certain circumstances you would want to prefer one to the other?
Actually, this C-line method is not very common in design. The two common ones is gonna be, this is gonna be the one, right? The basic concept and the balanced load, because you'd like to shoot for a certain amount of load that you need to balance for. And this is gonna be up to you. You can pick and choose the method that you wanted. So most likely you are gonna be using this method, right? The basic concept, and also are gonna be using this balanced load. So actually in the analysis, I'm gonna skip this because this is not really critical, and I mean, it's so simple. You can figure it out yourself if you want to. Just a couple of slides if you want to read it. It's not important to me. I'm not gonna be asking you questions on it, but usually I ask questions on the basic concept method, which is this one here, and the balanced, and the balanced load method. Now let's look at the balanced load method and see what can we do about this. I need to find out how much is the balanced load, right? Eventually, I'm gonna have this amount of pre-stress force, which is this piece of E effective, right? You guys remember this number here, 229.5 kips at the minute span?
Yes.
And I know that the amount of eccentricity given in the big table is 14.77, and I can put it in feet if I want to. When it comes to the balanced moment or the balanced load method, I'd maybe better put dimensions in feet, just to make it simple for me. But keep track of units. I'm gonna say here the balanced load, I can figure it out by setting the external moment equal to the internal moment. Or I can just use this equation. WB is gonna be 8 PA divided by L squared. So the moment that I can balance here, according to this equation, is gonna be 552 pound per linear foot. So for this given force, this force here is pushing up by 552 pound per linear foot. Let me see here the total load. The total load that I have is going to be W dead load given in the section properties plus superimposed load plus live load of 420. This is going to be the total. You remember our example when I say 2 kip per foot, right? And they have total of 3 kip per foot. How much was left? Okay, say 1 kip per foot is going to be unbalanced. So here I'm saying the balance is 552. Total 779. How much is unbalanced? It's going to be total subtracting the balance. It's right here. It's going to be 227. At the balanced load, how much was the stress? It just was equal to P over A, right? At the balanced load, your stress in the beam is going to be P over A. So, okay. How about at the service load? You guys see at the service load is going to be equal to P over A. I'm going to say plus or minus M unbalanced divided by S. I'm going to go back here to slide. I know I'm at 36. I'm going to go to this one here. I'm going to say stress is at the balance. It's going to be right here. Slide 19. The stress on the top is going to be equal to P over A, and then you add the effect of the unbalanced moment. What's the unbalanced moment? It's going to be equal to unbalanced load times L squared divided by 8. So I'm going to go back here. Here is unbalanced load times the span squared divided by 8. Again, multiplied by 12 to put it in pound-inch. Now, how much is the stress on the top? In the top, this moment is causing compression, right? So I'm going to be following this equation here. It's going to be P over A subtracting M unbalanced divided by S top. And look at this, compression, 898. Compare it to the previous example. Exactly the same. You need to end up with exactly the same number. Otherwise, something is wrong. Same thing in the bottom. Now, this unbalanced load is going to be causing tension on the bottom. So again, it's going to be P over A plus this moment divided by S bottom. It's going to be tension, 594. I can take you back here and just show the numbers. It's gonna be 594. If there is a difference of 1 psi in number, it means something is wrong in your analysis. Are you guys good?
So basically, with all the givens that we get, we could basically choose what method we want to use to solve, or would like you ask a question where you specifically want us to use a certain
Once
method?
you see the question, you will figure out which method to use. You know it yourself.
Okay.
Professor, can you go back to the unbalanced load? Where the question was? No, yeah, that's that page.
Yeah.
So that 5, can you explain that 552?
Okay. Where's the 552 coming from? You put certain amount of pre-stress force on the beam, right? And that is equal to 229,500. You know where it's coming from, right? Right? You can say, yeah, okay, let's look at it, where it's coming from. 229,500 is actually P sub E. And if you see here, I use it here, right? This is gonna be 229,500, roughly. It's gonna be right here.
Oh, okay.
1.53, which is the total cross-section area multiplied by 150 KSI. You're gonna be getting this number, right?
Mhm.
This number here, you're gonna say if you multiply by E, you know what is E, right? E is
Mhm.
this eccentricity. But of course, you need to be careful, you put it in feet. It's gonna be here the internal moment, resisting moment. And then you say it's gonna be equal to W squared over 8. Let me show you. You're gonna say this is here equals W squared divided by 8, which is this equation here. So WL squared divided by 8 is gonna be equal to P times A. Here's A, the eccentricity. It's gonna be the force,
Oh,
EE,
okay.
right? So with that, the balanced load here is gonna be 552 pound per linear foot. This is what you need to balance.
Okay, got it now. Thank you.
No problem. All right, so let's see the homework. What homework do we have?
Professor, can I turn the homework in after class?
You cannot because it's closed. I need to open it for you. Anyone else want to submit after the class? Anyone else? First time. Anyone else? Second time.
I'm the only slacker here.
Okay. All right, Chris. I'll open for you.
Thank you.
No problem. So in here we have simple pre-stress beam that you guys have seen already, right? So you know how to find out the moment of inertia. You need to find out its top, its bottom, and all this nice stuff, right? It says here the total superimposed dead load on live load is 0.4 kip per foot. How about the self weight? Can you figure out the self weight of this beam? Can someone help me with this? Self weight. How do you do the self weight of this beam per linear foot? No? Yes? No? Any log? Yeah, based on the unit weight. How much is the unit weight in this case? Say the weight of this beam per foot is going to be equal to 2 feet because 24 inch. Or I can say 24 times 16 divided by 144 to put it in square feet times 150. It's going to be 400 pound per linear foot. This is going to be the self weight of this beam, right? Just happened to be the same as this. This is going to be 400 pound per linear foot.
This beam is lightweight, right?
What?
It's the lightweight concrete we're using, right?
Is this lightweight? Does it say lightweight concrete?
Because the 150, you got it from my previous
Normal weight.
Oh, normal weight?
Maybe
Okay.
for normal weight, right? If it doesn't say lightweight, please use normal weight. It says here the used pre-stressed cables are this gonna be this. How much is the cross-section area for this cable? Anyone remembers? For one cable, right? Do you know how many cables? Does it say how many cables in here? Does it say how many cables?
No.
Is it one cable? No.
Looks like one cable.
No. In pre-stress, we just show something like this, but you're gonna have more than one cable, right? It's just the P force, but doesn't mean it's gonna be one cable. We never show more than one cable in the picture, but it's gonna be more than one cable, okay? It says here, determine the effective pre-stressing force needed to balance 90% of the self-weight. How much is the balanced load in this case? I'd like to hear from you. Determine the effective pre-stressing force needed to balance 90% of the self-weight, 90% of dead load. How much again are we balancing? You can see here W balance. How much is that? How much you want to balance?
The P times L squared.
Great.
Or
How
A.
much load do you want to balance as in pound per linear foot? Based on the statement here. Based on the statement here. How much is the balanced load?
400?
What?
90%?
90% of what?
400?
Of dead load.
To 400? How much is that?
360? No.
Yeah.
360.
Okay, so it's gonna be 0.9 times 400. This is gonna be my balanced load. I'd like to balance this much. Am I correct? That's what it says.
Yes.
The balanced load is gonna be 90% of the self-weight. I don't want to balance the entire dead load or self-weight. I'd like to balance only 90% of it. Are you guys listening? Yes? No?
Yes.
Okay,
Yeah.
very good. Now, how much point load that you'd like to put here in this case? You say, well, depends on the span. The span is 50 feet. This is gonna be L, right? It's gonna be 50 feet. About the eccentricity, how much was the eccentricity? Can someone help me here? Eccentricity equals
8
what?
inches.
Should I
Eight
put
of-
in feet or in inches?
Feet.
Okay, 8 divided by 12, right? Feet. Now, how much force should I put to balance this?
WL.
How much is the external moment? W times L divided by 8. This is gonna be E, this is gonna be P. So this P is gonna be equal to the moment external divided by this guy. This is gonna be in pounds. Am I correct? This is gonna be the amount of tension force that I need to put there to balance how much? 90% of the dead load. Are you guys with me? I don't want you to struggle and not to gain any points on this homework. So please stay focused and ask me questions. We're good about this item here? Yes or no?
Professor, can you repeat the last part, please?
Okay. As I said, external moment is going to be equal to the internal moment. How much is external moment? It's going to be equal to 360 multiplied by 50 squared divided by 8. Because your target is to balance only 90% of the dead load. So I said, great. 90% of the dead load is going to be 360. The span is 50. External moment is going to be equal to W squared divided by 8, right? It's going to be this much. Pound what? Pound foot. Correct?
Yes.
This external moment equals to P times E. Internal moment. Therefore, the amount of force is going to be equal to the external moment times divided by E. because you'd like to set external is going to be the same as internal. Very similar to what we have done here. W equals 8 PA over L square, or PA equals W square over 8. You have the span, you have the weight, you have A, you can solve for P. This is exactly what I have done. We're good?
Yes.
Okay. Now it says determine the number of strands. Now, how many strands should I put? One strand takes how much for the total load? Do you know the capacity of one strand? Or no? How to find out how much force can you give to a strand? Can I?
Table.
It's gonna be 150 for each strand multiplied by 0.153, the cross-section area of one strand. You see this, 0.153. And the effective force is gonna be equal to what? Let me put it here. 0.153, which means this cross-section area, times 150,000 pounds. So each strand is gonna be taken this much, right? Now, how many strands? It says 7.35. Would you put 7 or 8?
8.
Why?
Seven.
This is a good question, right? Now think about it more, please, and then think about it and say, are we balancing minimum of 90% or maximum of 90%? If you balance minimum of 90%, it means you'd go to 8 because you're going to be balancing more load, correct? If you balance maximum of 90%, you're going to be going to 7 because if you go to 8, you're going to be balancing more load. Any questions on that? Yes or no?
Got it. We're balancing a max of 90%, correct?
You are balancing a maximum of 90%. So I'm going to put it here.
We're gonna go for 7.
So I'm going to say balance a maximum of 90% of the self weight of the beam. You need to be close to 90% because I don't want someone here to think I'm just typing it. I don't want here someone, I just put it there, right? I'm going to say maximum of 90% because if I say maximum 90%, 10% is going to be good, right? Someone's going to say, let me just add one strand. I'm going to be balancing only 10%. Well, still less than 90% because now this assumes to be 90%. So I'm going to say maximum and then you be close to 90%. And with that, you can figure out number of strands, which is this one here. So the effective stress force is going to be this answer, right? And the number of strands is going to be 7. Yes, go ahead. You have a question?
No, I just meant like 7 strands.
Okay. Now the third question says determine the actual effective pre-stress. What does it mean by actual effective pre-stress? How can I do this? So number 3. What is the actual? Are you saying that this number that I get here was not the actual, which is this number here? That was not the actual force? Or what? What is that number here? Is this the actual force?
Well, it's reduced by 90%, right?
This is what is needed, but this is not the actual. This is needed. And based on what is needed, I picked 7.35. Now the actual number, I'm gonna say number of strands is gonna be what? It's gonna be 7 here, right? P actual, P effective, which is the actual one, is gonna be equal to this multiplied by 0.153, right? Actually, it should be multiplied by how much each strand is gonna be taken, which is 22.95. So what is that number here? This is what is needed to balance 90% of the dead load. And this is what I'm gonna be providing at the end, which is the effective actual pre-stress force, effective pre-stress force. Why? Because I'm not gonna provide 7.35, I'm gonna provide only 7. So the pre-stress force, the actual effective one, is gonna be equal to 7 multiplied by how much each strand is gonna be taken, which is 0.153 multiplied by 150 KSI. We're good or no?
I think we're good.
All right. How about the initial? Initial is going to be based on what? What is the actual initial pre-stress force? I'm going to take you back here. Now compare the initial to the actual or to the effective. Difference is for the initial you use 189. So in this case you take 7 strands multiplied by 0.153 times this value here. I guess with that, I helped you with all the way to maybe number 4. Now we are going to be checking the stresses, top and bottom. And then you continue this business on your own. Any questions? Yeah, any questions before we close for today, for this evening?
No questions.
So for the submission of this homework, I mean, we're gonna be using an Excel file, but you want it all written out, right?
I want Excel file, but you need to show all the steps.
Oh, okay.
So it is, if you like to do Excel sheet, and remember this, you need to show the step here. For example, this equation says this times that, right? So we're gonna say this equation is gonna be APS multiplied by, is gonna be, let's say, FPS. You need to write it down. If you're not gonna write it down, I'm not gonna count it to be an answer. So
Gotcha.
like, you cannot just show it the way I'm showing it here. This is just for our solution. You need to type the whole thing. If you don't want to type the whole thing, you can just do the spreadsheet and then handwrite it if you want to, or type it, whatever you want. It's gonna be up to you.
Okay. Thank you.
No problem.
Thank you for helping us start it.
All right. Good luck.
And it's homework 4, right?
What's that?
This would be homework 4, right?
Yes, it's homework 4.
Oh, thank you.
Yeah, homework 4. You're correct. Homework 4. Just made the PDF out of it, and I'm gonna post it very soon.
Thank you so much, Professor.
No problem. Good luck. You guys have a good night.
Professor, can I ask you a question?
Yeah, go ahead.
So I found out the last homework. This is a question regarding
I
so
have your kind of your voice is not. Yeah. Go ahead. What?
Is that better, Professor?
Yeah, much better now.
Okay. Yes, I was just wondering. So for the last homework, you had like at the end of the beams, the tendon went through the centroid of the section,
Yeah.
and at the center it was 4 inches from the bottom. So when we were doing for example, just the stresses due to the loading at the end of the beam, there's no moment according to the moment diagram at the ends of the
Yes,
beam.
there's no. This is correct.
So it's literally you just have a constant compressive force due to the tendon being through the
Exactly.
centroid.
Yes. This is
Oh, okay. All right. I was yeah, okay. And then another question was so the answer that I got, the effect of the pre-stress, it wasn't like that big. Was it like supposed to be that big? I did get that the compression at the top went down a little bit and the tension at the bottom also went down a little bit at the center of the beam. I just, yeah, just when I drew it out, it looked like the effects of the pre-stress was just very small.
okay.
Um,
This is fine.
oh, okay, that's fine. Okay.
This is fine. Absolutely. This is fine.
Okay. And then uh okay, I think that's good. Thank you so very much, Professor.
All right. No problem. Good night.
You too.